Yeah, I'm very happy to give a talk here today. So I will talk a lot about ideals, and whenever I say ideal, what I really mean is a normal uniform ideal on omega 1, just to save some time. So I will start with a little bit of history, then a theorem, and then a mystery. Let's see, so there are a number of nice properties you can put on ideals on omega 1. Let's start with precipitousness. So what does this mean? Let me give you a quick reminder. So whenever you have an ideal I, then you can form a nice partial order, which is just the power set of omega 1 modulo the ideal. So the inclusion induces a nice partial order on there, and you throw away the least element, the equivalence class of the empty set. And you can force with this, and this gives you some kind of generic ultrafilter on omega 1, generic V ultrafilter on omega 1. And precipitous means that if you force, then you get a generic ultra power. And the point is that this is well-founded. So that's a property. And so the history for precipitous ideals is that Mitchell proved in the 70s that you can force a precipitous ideal from a measurable cardinal. So what you do is you have the measurable cardinal kappa, you collapse it to omega 1, and sort of the fragment that's left of the ultrafilter generates a precipitous ideal. Okay, and always when you can get some ideal with a nice property, you can ask about the canonical ideal on omega 1, the non-stationary ideal. And a little bit later, Magidor showed that he built upon this method here that you can get the non-stationary ideal precipitous from the same assumption. Next, very important prominent property is a saturated ideal. This means that the forcing here has a nice chain condition, the omega 2 chain condition. So it's a strengthening of precipitousness. And Kunin was the first who showed that you can get a saturated ideal on omega 1. And the assumption used is a huge cardinal. And then later it was shown that you can also get the non-stationary ideal to be saturated. So the first instance of this was by Steele and Recep. You can get the non-stationary ideal to be saturated. And the interesting thing here is that this was not a forcing over a ZFZ model, it was forcing over a determinacy model. So, but you get a model of ZFZ in the end. So I guess the intuition behind there is, what does AD have to do with these questions? Under AD, omega 1 is measurable, and then you may hope that AD gives you enough tools that you can extend to generic extension, forced choice, but maintain some kind of property of omega 1 which is close to being measurable. And saturated is somewhat close to being measurable. So an interesting thing here is, by the way, that this was done before it was even known that AD was consistent from Dutch cardinals. This is still baffling to me, how you can come up with such an intricate construction when you don't even know that it's consistent, AD. Anyway, so later on, Foreman, Magidor, Scheller showed that you can get the non-stationary ideal to be saturated from a supercompact cardinal. And this is again forcing over the ZFZ model. And the nice thing here is that you preserve omega-1. You even have a stationary set preserving forcing. So via stationary set preserving forcing. And later the assumption was reduced by Szilard to the optimum one, which is just one wooden cardinal. So the next thing, the next strengthening is an omega-1 dense ideal, which means that the forcing pi has a dense subset of size omega-1. And here the results are all due to Wooden that I'm going to mention. So Wooden showed that you can force some omega-1 dense ideal from an almost huge cardinal and he also showed that you can get the non-stationary ideal to be omega-1 dense. But this once again is forcing over a determinacy model, let's say L of R. L of R under determinacy. Okay, but if you can only force it over AD models, that's sort of, or in this instance, some canonical AD models, that's some sort of restriction to the method. And if you are familiar with the omega logic and the omega conjecture, then this method of Wooden actually shows that the statement the non-stationary ideal on omega-1 is omega consistent. So if you believe in the omega conjecture, then it should also be omega satisfiable. And this does not give you that it's omega satisfiable. So the corresponding question is, can you also force it over ZFC? So Wooden formulated the following question. Assume large cardinals, whatever you like, and then is there necessarily a forcing which forces non-stationary to be omega-1 dense, and to even ask for a specific property. So the forcing from Maigret-Scheller is a stationary set preserving forcing, and he asks for the same property. Is there stationary set preserving forcing P such that in the extension the non-stationary ideal is omega-1 dense? Okay, so that's the history. Here's the theorem. Yes, you can do it. Okay, I will tell you the large cardinal assumption that I have. So assume that there is an inaccessible cardinal kappa such that kappa is a limit of less than kappa supercompact cardinals. And then there is such a forcing. Okay, so now you may ask what's going on here. You're using a lot of large cardinals. Okay, why are you doing this? So there's something strange going on here, which I don't really know how to make proper sense of this. So here's a fact. Due to Wooden, you cannot prove this theorem without assuming at least a Wooden limit of Woodens. You need at least a Wooden kernel, which is a limit of Wooden kernels. But consistency-wise, the statement NS omega-1 is omega-1 dense. It's just omega many Wooden kernels. So somehow you need significant.
So you're going to explain what you mean by this sentence?
Well, so it means that there is from if you assume less than a wooden limit of woodens, then there is a model with this amount of large cardinals, and you cannot force the non-stationary ideal to be omega-1 dense with the stationary set, even omega-1 preserving forcing. So this is what I mean by this. Over that model. Yeah, so really you cannot prove this theorem in this generality without assuming at least a wooden limit of wooden cardinals. Okay. So yeah, in my view this is quite mysterious. I mean, I understand the proof why this is the case, but it's still strange. This is the mystery. So here's maybe a bit of a hot take. So Gregor had some nice bold conjectures in his talk. I think that's a good thing to do, to make a few bold conjectures. So I would say that you will need even more than this. So now it depends how brave I am, how much I want to claim. Okay. Let's say you need at least a super strong cardinal. If I would have been a little bit braver, I would have gone up to more super compactness.
That's the bravest you can do.
Well, I'll stick with that. But yeah, I think it doesn't really matter what I put there. In any case, I think it will be really difficult to either prove or disprove the conjecture. Even with super strong or super compact, I've got no clue. Okay, anyway, so for the rest of the talk.
So what is the conjecture based on? Like, is it the Woodin's argument or?
So yeah, the fact that you definitely need significantly more large cardinals than you think you would need to do it. And well, the rest comes really from actually the proof, how you prove the theorem. Like the large cardinals are really completely embedded into the argument in a way that, yeah, it seems very difficult for me to.
What do you mean by this equality?
By this I mean that that ZFZ plus NS omega-1 is omega-1 dense is equiconsistent with ZFZ, and there are infinitely many wooden cardinals. So the consistency strength of AD. Yeah, that is due to wooden, this equiconsistency. Okay, so for the rest of the talk, I would just like to explain a few ideas here, how to prove the theorem, and I would like to explain why you need new methods to prove this theorem. Okay. So how does the forcing P that does it in the end look like? You can make an educated guess how maybe the rough shape of it could be. So a good guess is that P should be some kind of quadruple support style iteration. Let's say RTS iteration of length kappa. Of, let's say at least omega-1 preserving forcings. And then in the end, what should happen is, so you have omega-1, it should stay omega-1. And here you have your large cardinal kappa, and in the end, it should become omega-2. And well, you can even say a bit more, like all the initial segments, the initial factors should have small size, all of small size, and these kind of things. So why would you make this guess? Two reasons. The one is from the NS omega-1 saturated case. So the forcings which force NS omega-1 is saturated over ZFZ, they look like this. Okay, so and omega-1 density is of course a strengthening of saturation. And the next thing is that and then plus plus implies star. This results strongly suggests that that there should be a forcing axiom behind this that implies that the non-stationary ideal is omega 1 dense. Suggests, so there is a forcing axiom which is very strong, which is roughly similar in strength to m++, and it implies the statement that the non-stationary ideal is omega 1 dense. So yeah, before this result, I don't think there was a good reason to believe in this. If you look at the non-stationary ideal being omega 1 dense and its consequences, it doesn't really look like a forcing axiom. It implies that there's a Suslin tree, that there's a meager set of a non-meager set of size omega 1. Like almost disjoint coding doesn't work. MRP fails. A lot of things that maybe some of them you would expect. But this result, if you look at it correctly, definitely suggests there should be such a thing, and indeed it turns out that there is, but I will come back to this later. Okay, so the point is, if you believe that the forcing looks like this, then the forcing, this iteration, cannot be an iteration of stationary set preserving forcing. So that's the key point. P is not an iteration of stationary set preserving forcings. So what is the reason for this? So we start here, 0, here you have V. In the end, you iterate all the way up to kappa. You have Vg or Vg kappa. And in the end, you want that the non-stationary ideal is omega 1 dense. So there's a witness for it. So here, you have a sequence of omega 1 many stationary sets, which provide the witness for the statement. And this is really just a subset of omega 1. For abstract reasons, this forcing will have the kappa cc. So this subset, so this sequence here will already appear in an earlier stage. Exactly. So there will be an alpha here, and this thing here is actually already an element of Vg alpha. Okay, but there's now absolutely no reason to believe that already in here, this thing is a witness to the non-stationary ideal being omega 1 dense. Okay, so it means that you have some stationary set here, and none of the SI are contained in it modulo this non-stationary ideal. The only way to fix this is to kill a stationary set. There's no other way. So the iteration from here to here is not stationary set preserving. So in this again, once again, by the kappa cc means you must have used forcing along the way, which is not stationary set preserving. Okay, so this is sort of the abstract reason. And this is the reason that some new method is necessary because well, there's no iteration theorem in the literature. You need some kind of iteration theorem, of course, to make sure that at the very least omega 1 is not collapsed along the way. And there is no iteration theorem in the literature which allows for this amount of stationary set killing. I mean, there are even some abstract reasons why you cannot have too many stationary sets killing in an iteration without collapsing omega 1. How much time do I have left? 5 minutes. Okay.
How do you get to this special family Fi number?
Okay, you add it generically. You force diamond in a nice way, and then, well.
You add them right away at the start.
Yeah, so in the end, alpha will be 1. Yeah. So in the end, the whole forcing P will be stationary set preserving. You will do one step, which just forces diamond. You add this thing, and then for the rest, you will aggressively kill stationary sets for the whole time. Okay, so we need an iteration theorem. And it looks like this. It's a little bit strange, but it tells you that the situation there is roughly possible. So assume P iteration as before. And you put 2 restrictions on it. Maybe the first thing is that for all alpha less than kappa, you want that at least P alpha whatever plus 2 or plus 7, I don't really care. Force is a strong reflection principle. I will explain why in a second. And the second thing is that the iteration only kills fresh sets. You kill only fresh stationary sets. So this means for all alpha less than kappa, if you already force with p alpha, then the next forcing you use should preserve stationary sets from the previous stages. Okay, so these are the two restrictions. And then in the end, the forcing you use P preserves omega 1. That's the point. So these two restrictions are really necessary. Why is this the case? Well, there are two counterexamples. Why do I force SRP all the time? So you need to use at least sufficiently often, in some sense, regular forcing. So what do we mean by regular forcing? I mean, for example, that semi-properness is sort of the regular notions of being stationary set preserving. And you need something like this for general omega 1 preserving forcings. Okay, and so this kind of property exists, and all omega 1 preserving forcings will have this property under SRP. So we just force it a lot. And why do I need the second thing? Is because there's a very stupid counterexample. You just split omega 1 into omega many stationary sets. Yeah, you kill one by one, and then it doesn't matter what limit you take after these omega many steps, you will definitely collapse omega 1. Okay, but the problem here is that you all the time you go back to V and kill a stationary set from there. So you should forbid this. You should not be allowed to go back to kill a stationary set.
So the conclusion is just that P preserves omega 1, or that it's
No, I mean, the first forcing you use could just kill a stationary set. I don't forbid this here. So no, the conclusion here is really that P just preserves omega 1. Yeah, so this is the kind of iteration theorem you need in the end to prove a theorem.
Why you cannot push SRP to something more?
Well, it hinges on a trick in the proof of the thing. That you really need sort of SRP up to where you up to the length of the iteration, sort of. So you really need SRP always at least up to kappa. Not full SRP, but SRP up to kappa, let's say.
No, I mean, can you get MRP? Can you force MRP up to kappa?
Well, I don't see how this suffices for the argument.
Is there MRP utilized SRP?
Sorry, say again?
So, I mean, the version of MRP but not running to love for project decision is set to utilize SRP.
Okay.
Is it stronger? Can you continue with that? Definitely you have SRP, can you force it back?
Yeah. Well.
Finally, you have SRP up to kappa.
Yeah.
So you will have MRP up to kappa.
Yeah, that's true.
Not MRP for enough. On project decision is inconsistent.
Yeah, you cannot have MRP with a non-stationary being omega 1 ends. But maybe we should continue the discussion afterwards. So, okay, do we have a few more sentences I can say? Great. Okay, so now I will just roughly say, I just told you sort of one method you need to use here. The other completely different thing is which forcings do you really use in the end. So if you know the proof how to get the non-stationary to be saturated, you have these ceiling forcings you need to iterate. And here you need sort of a version of the ceiling forcing, but to get the non-stationary to be omega 1 dense. And well, there is a natural candidate which seems to be very natural in this instance, and it is a version of the MM++ implies star forcing, but you have to do a bit more. So you first add this add this witness here. And then you have this version of the MM++ implies star forcing, which always tries to make the non-stationary ideal to be omega 1 dense, at least remove some counterexamples, or the counterexample that we currently have. You have to do some things, some non-trivial things to modify it. So you have to replace Pmax basically by Qmax in the argument. And if you just try to do this, there are two significant problems which arise, and you have to solve them. Finally, everything works. You can fit everything back together, and then iterate up to the large cardinals that I proposed at the beginning. Okay, I think we have to go get lunch, right?
Are there questions? I have one. Well, you say you have to preserve stationary sets from the previous stages, but I guess when you add SRP, you're adding many new stationary sets, and then what you do, you kill them all right away at the next stage.
Yeah.
So in one stage you are killing a lot of stationary sets.
Yeah, exactly. And you have to do this, and this makes it difficult to find the right forcing again.
At stages you force SRP, and at even stages you kill all the new stationary sets that you have added with SRP.
Basically, yeah, all the counterexamples, you have to do it in a coherent way.
Yes.
Yeah.
Okay, thank you. Other questions?
You said that when you were talking about using SRP, you said that you need something that it implies. Does it need to be SRP, or it's something that SRP gives?
Well, in the end, it's something that SRP gives. So SRP. I don't know, but so under SRP, all stationary set preserving forcings are semi-proper, and there is this other strong regularity property which works for all omega 1 preserving forcings. It's much stronger than semi-properness, and you need that all omega 1 preserving forcings have this strong regularity property. This is what I really need.
And does that imply? I don't know. Does that say anything? Does that property by itself, or from the stricter form of it, say anything about NS omega 1 is omega 1?
This alone, no. No, unfortunately not. I mean, it says, it probably implies that non-stationary ideal is pre-saturated, but not more, I would assume.
Other questions? Okay. No? Okay. Before clapping for the last time, remember the sheet about the lunch of tomorrow and of Friday, and the dinner of tomorrow and of Friday. Please fill it before this lunch. Okay, let's thank Andreas once again.